Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we will discuss the AASHTO method of pavement design. This is lecture number 2. So now, what is an AASHTO method? AASHTO stands for American Association of State Highway and Transportation Officials, and this pavement design procedure is based primarily on the results of the AASHTO road test that was conducted in Ottawa, Illinois, US. It was a cooperative research carried out under the auspices of 49 states, the District of Columbia, Puerto Rico, the Bureau of Public Roads, and several industry groups. So the AASHTO method is a regression method based on the results of road test. The AASHTO method utilizes an index term, the structural number, to indicate the required combined structural capacity on all pavement layers overlying the subgrade. The tests were conducted on a short span bridges and test sections of flexible and rigid pavements constructed on A6 subgrade material. Those of you who doesn't know the meaning of A6, A6 material is a clay or silty material, or you can say the worst type of material, and it is the material that the pavement engineer doesn't like to have while constructing a road pavement. Now the pavement section consists of two small loops and four larger ones, each being a 4-lane divided highway. The tangent sections consist of a successive set of pavement length of different design, each lane being at least 100 feet. The principal flexible pavement sections were constructed of asphalt concrete surface as well a graded crushed aggregate limestone base and a uniform graded sand gravel subbase. Three levels of surface thicknesses ranges from 1 to 6 inches were used in combination with three levels of base thicknesses ranges from 0 to 9 inches. Each of these 9 combinations were then combined with three levels of subbase thickness ranges from 0 to 6 inches. In addition to the crushed limestone bases, some special sections had bases constructed with either a well-graded crushed gravel, a bituminous plant mixture, or a cement-treated aggregate. I can understand that the word cement-treated aggregate is not known to you. It's just like it's just like a lean cement concrete. But the difference is, in case of lean cement, lean concrete, the cement and aggregates are mixed together before laying, while in cement-treated aggregate, the aggregates and first the aggregates are laid, and then a slurry of cement water is applied on it, and then it gets compacted. So that is what we call a cement-treated aggregate. The test traffic section of both single and tandem axle vehicles were then driven over the test sections until several thousand load repetitions had been made. Until this point, since we have not explained single axle and tandem axle, just this is for knowledge, and obviously along as the lecture proceed, will define for you what is a single axle and what is a tandem axle vehicle. Then 10 different axle arrangement and axle loads combination were used with single axle load ranging from 2,000 to 30,000 pounds and tandem axle range from 24,000 to 48,000 pounds. Data were then collected on the pavement condition with respect to extent of cracking and amount of patching required to maintain the section in service. The longitudinal and transverse profiles were obtained to determine the extent of rutting, surface deflection causes by load vehicles moving at a very slow speeds, pavement curvature at different vehicle speed, stresses imposed on the subgrade surfaces, and temperature distribution to the pavement layer. These data were then thoroughly analyzed, the results of which form the basis of the AASHTO method of the pavement design, that is what being practiced in the industry today. This is a layout of AASHTO road test. You can see there were 6 routes as I have discussed, and it is this 178, 71, 23 is usually the route numbers assigned to different roads in a USA highway center. Uh, if you enlarge each of that loop has a flexible test section and a rigid test section, then there is a turnaround connected by steel high beam bridges. Now, what was the major finding of this test? There is a concept of serviceability, the effect of pavement thickness on performance, and as a result, a AASHTO 1993 pavement design guide was developed, and it is now being used as a reference material for designing pavement mostly all over the world, but in Pakistan we use this pavement design guide. What were the limitations? These tests were conducted in USA. The climate and subgrade materials are different, and at that time the experimental performance, the road was tested on a very low traffic level. It is not the traffic level that we are experiencing nowadays. So these were the shortcomings. Now, if you are interested in designing a flexible pavement, you have to follow the following steps: pavement performance, road bed soil, estimate the reliability, assume standard deviation, calculate traffic, input material properties, what are the drainage values, you need to define it, and last but not least, you will calculate the thickness. That is what the design is. Now we discuss what is a pavement performance. AASHTO pavement performance is defined in the terms serviceability, and the word serviceability, it's a number that ranges from 0 to 5, describing the pavement condition. There is always an initial serviceability, that is the condition of the pavement immediately after construction, and then there is a terminal serviceability, the point at which you feel the pavement is failed either functionally or structurally. The values for initial serviceability is 4.2 for flexible pavement, and the value of terminal serviceability is 2.5 or 3. Now, if you draw a graph between PSI versus time or serviceability versus time, you will find this behavior. Now, what is this behavior? Now, this is at time 0, that is when the road is open to the traffic. It has an initial serviceability that is 4.2. And with respect to time, the road condition deteriorates, cracks begins to appear, and the serviceability level decreases to the point that what termed as terminal serviceability. Remember, this curve is a this curve is not a linear curve. So that means the the reason for this deterioration are different, are many. For instance, the temperature variation, the traffic variation, or the performance, or any other thing such as the performance of the material that we were expecting were not good enough. Anyhow, when this point reaches, what we do some treatment to the pavement and make it serviceable again. As I've defined, this serviceability, it's a scale from 0 to 5, where 5 means very good and 0 means very poor. Normally, if your serviceability level is between 1 to 2, we consider this pavement as failed. And if it is between 2 to 3, we need some repair. We have different levels of terminal serviceability. For instance, we are designing an RTL, it is 2.5. For collected road, 2.25. 2 is the residential street, and 3 for a motorway or a freeway. So, what is the correct design? Now you can see that there are 3 levels of curves. If your pavement is still serviceable at the end of the design life, then you may have over-designed it. And if your pavement serviceability index has reached its terminal serviceability before the design life, then it means you have not designed the pavement correctly. Obviously and ideally, the pavement shown as a clean line performance the correct pavement design. Now, what is that time period? 30 to 50 years, 20 to 50, 50 to 25, 10 to 20. But mind you, in the last lecture, I said in Pakistan, normally we go for only 10-year design period. Now, the second input in AASHTO Flexible design is the subgrade value. So, what is a subgrade? A subgrade is made of native soil that has been compacted to withstand the loads above it. It can also be defined a layer required in many structures such as pavement slabs, although it needs to have certain characteristics. Another way of defining subgrade is that a subgrade might need special drainage structures to let water if it is composed of impermeable soil, and it should be graded to within plus or minus 1.5 inches of the specified elevation. What I mean is whatever is your subgrade, you raise it to at least 1.5 inches to a specified elevation. Now, the strength of this subgrade is estimated in terms of California bearing ratio and a resident modulus. Before I move ahead, let me tell you the difference between a California bearing ratio and a resident modulus test. California bearing ratio is a uniaxial test. That is, while testing the subgrade material, we apply only vertical load and calculates the deformation. While in terms of when we perform resilient modulus test, it is a three-dimensional test. So that's the main difference between California bearing ratio and resilient modulus. Despite the advantage of resilient modulus test, it is to be noted that the resilient modulus tests are costlier tests. So what we do is we perform California bearing ratio and then convert into the resilient modulus value by using some relation as established by AASHTO method. So what is CBR? Actually, it is developed in late 1930s, and as I've said, it is resistance to the material to uniaxial penetration. It measures the strength to standard crushed stone material because ratio means comparison. It can be performed in field and in laboratory. Most of the pavement design method used, and not only the subgrade strength is estimated, but the other layer like sub-base layer and base layer are also estimated by CBR values. The common test equipment that are used is a CBR mold and a testing machine, and then what we do is a very simple method. You take the cylinder, you take the soil, normally sieve through number 4 size. To compact the soil in cylinders in semi-layers, wait, and then before putting it into the machine, you place extra weights on it. These weights are technically known as a surcharge weight. Surcharge weights simulates to the dead weight of the pavement. There are two types of CBR test. One we call as a soaked test, the other is called unsoaked test. The difference is that in a soak test, we soak the sample 4 days and then we put it in the machine and test the CBR value. While In unsoaked test, as soon as we prepare the sample, we test it. But practically, unsoaked value has no significance in pavement design. So when we been asked to give the data of CBR for pavement design, we always give a soaked CBR value. So let's see how it is performed. You can see at the soil sample, and there is a load, piston, load that is applied through a piston that is 3 square inches. And what we do, we apply the load at 0.05 inch per minute and record the load at every 0.1 inch penetration. We keep on doing it until we reaches 0.5 inches, or if the sample have failed before 0.5 inches, then we obviously stop. Once we collect this data, we draw a load penetration curve that is being shown in the next slide. But before we draw a load penetration graph, we can convert the value of load obtained by dividing it 3 sketch square, and before calculating CBR value, we need to know what are the standard values of CBR for a crush row. So the load of standard raw obtained for CBR is 3000 for 0.1 inch penetration and 0.2 inch for 4500 penetration. The other values are in terms of stresses. But you must be imagining that the simple mathematical rule says if the penetration is 0.1 inch is 3000, the penetration at 0.2 inch must be 6000. But it is not the case. Why? Because the first 0.1 inch, there is a load that what we call a seating load, or the load that is required to penetrate to the surface. Once that penetration is created, obviously we will require less load as that can be shown in the table as well. Remember, we calculate CBR at 0.1 inches and 0.2 inches, and whatever is the maximum value we used as a design CBR, and we forward it to the pavement designer. So what is the load penetration curve and what are these behavior? We go one by one. On the x-axis, this is penetration. As I've said, that we stop at 0.5 inches. Now this is the load, right? So the load in the first curve, as we start loading the material, it increases gradually, and then at some point it goes down. And if we proceed further, this will go up. So what we can see is that there is a problem with this curve. Why there is a problem? That the behavior of this curve is not consistent. It should be either decreasing or increasing. It is not like this First it got decreased and then it got increased, then it got decreased. So this is not a curve. So what would have happened? The answer is simple. Maybe uh, a value error in writing the values, or it may be something else. So if you obtain this curve, this CBR value cannot be used for, for further elaboration. Now let's see what is this blue curve. This blue curve is an ideal curve, and it is what a desire of our pavement engineer is. See what happens. As you go, keep on increasing the penetration, the load resistance is increased, and it is increasing, and at 0.5 inches we stopped. Now this is what we call the standard curve, and again this may be an ideal situation. Normally what happens is this red curve. You see this reaction is slow at the beginning, and gradually it keeps up and then becomes parallel to the blue line. So what does this mean? This means that initially the soil may not have taken the load as it was expected. So this curve is acceptable, except we need to apply some correction to it. But before I go further, what is the reason behind this curve? This is simply that initially the soil top surface may be wet enough, and this has caused a slow reaction. And maybe while we were testing the sample, the piston have not touched the sample, and we have started testing. So anyhow, this can be corrected as it can be shown in the next slide. How you correct a curve? So this is the curve. What you do, you draw a tangent, and the tangent is drawn from the point where the curve change its shape. And then you extend this tangent to this point. Now we can say that the zero value has shifted. Now what we do, we start taking zero, and from scale you can see 0.1 value and 0.2 value, and these loads will now be used in the relations shown to you as compared to standard PROF, and the CBR value in percentage will be calculated. Then it must be noted that CBR is greatly influenced upon the moisture value. So while testing CBR, the material should have been tested for optimum moisture content. I feel this is an advanced topic that you will learn in your next year. So let it be like this, that what happens that you will have, if your moisture content is low, you will have a CBR value, and if you have low, the moisture content is high, for the same sample you will get less value. So beware of the optimum moisture content. This CBR value should always be tested at optimum moisture content. Now these are some typical values. Now, if your soil CBR is 10, it's a very good soil. It's a gravel soil. Then if it is fair, if it is between 5 to 9, it's a fair soil. Again, you will not have more problem in the designing the pavement. Although there is a clay something, but it will not be as bad. But if the soil is between 3 to 5, remember, most of the people says that you should not design pavement on a poor soil. That is, have the soil having a CBR of 3. So, what you do in these circumstances, you remove that soil and replace it with some borrowed material, and then you can use this soil. Nowadays, there are other ways to improve the strength of the soil, such as laying a geosynthetic material. Now, the second type of resilient modulus test, as I've told you, that it is a three-dimensional loading test. You can see it's a cylindrical sample and the loads are applied from all around. Resilient modulus is just like an elasticity modulus. And what if I ask you what is the elasticity modulus? Is simply stress to strain, but here the word deviator stress is being used. It means the difference of stress 1 and stress 3 divided by recoverable strain. What is a recoverable strain? Is that whenever the load, a soil is not a perfect elasticity. How you define elastic material? By elastic material, I mean that if the load is removed, the sample will recover itself, just like a rubber band. When it is stretched, if you just leave it, it will come back to original position. But a soil, some of the elasticity is lost. Means whole length of the soil is not recoverable. So that we call as a plastic condition. So what you do during test, to ignore that plastic behavior, plastic strain, and you only note that recoverable strain, that strain that is recovered after a removal of the load. So that is what we call a recoverable strain. Now, what we do? We determine the load carrying capacity of the material. This can also be used for asphaltic material as well as for any unbound material like subbase, base or subgrade. It is a repeated load triaxial test, meaning that the loads are applied from all three directions and we applied number of load tests. We keep on repeating the load, then removing the load and noting the strain. Till the time the sample is not good enough to take the load. And this time is shown when the sample get cracked. So this is resilient modulus, and it is the most acceptable value of subgrade that is taken for the pavement design nowadays. So if you don't have the facility to to then to test the value of resident modulus, you can estimate from CBR, and this value is given by this relation. That is, MR is 2,555 times CBR power 0.64. So whatever value is CBR you obtain, you put it here and you can find resident modulus. The unit of resident modulus is, as I've said, it is the same as of Lorentz modulus. So it's PSI or megapascals. Normally, the values are 3,000 to 40,000 PSI. Right? Now, the last topic of today's lecture is the reliability and standard deviation. So what is a reliability? It is some sort of assurance that the pavement you have designed, say for 10 years, will survive for 10 years. Is take the values of reliability is taken in terms of Z-score. What is a Z-score? It's a normal curve, and the values of Z-score is taken on left side of it, and it depends upon the standard deviation. So typically, if you will assume the higher design reliability, you will have a thicker pavement, and you design a less. If you take a lesser reliability level, then your pavement will be less thicker. Normally, you take 90% of reliability, and this is actually a factor of safety. Now, these are some typical values taken for different types of road. But in Pakistan, we take 95% to 90% reliability. This is the standard feature. And then when I was saying there is an AASHTO design, how they use this reliability, they use in terms of normal deviate, that is derived from this normal distribution curve. If you like to define ZR, it's a 1Z score, and it is used here, and the value is negative because we are using the left side. You must be wondering why we use the left side. It's because the overall effect of standard deviation and ZR is negative on the pavement thickness. That's why it's negative. Standard deviation. It accounts for the chance in the variation in traffic prediction and normal variation in pavement performance. Why we need standard deviation? It may be because of poor traffic prediction. For instance, we assume that the traffic growth will increase by 4%, but in actually case, it may have increased 5%. The material availability means we said that this is a material that have got CBR of 50. But what happens that the material's variability, material would not have a value of CBR 50. It may be 40. So then we need to address that issue. Then there is a construction variability. I mean, by construction variability, maybe there are people who are standing or responsible for construction of road, but they may not have enough training to supervise this project, or there may be problem with machinery that is being used. So this is all again a safety factor to address the unpredictability of the pavement. Normally, a AASHTO value is taken as 0.35 for rigid pavement and 0.45 for flexible pavement. Again, the difference is because the pavement, rigid pavement have less variable section. As I've shown you in lecture 1, that rigid pavement has normally 2 layers while flexible pavement is 4 layers. So there is a chance of greater variation in each layer of the pavement. So if you're designing a pavement, you can take the value of 0.35 for concrete pavement and 0.45 for an asphalt pavement. And if you are designing the overlay, then it will be between 0.39 to 0.49. And that ends my lecture. Hope you have enjoyed and you have understood fully the concept of pavement design. Obviously, this will be continued in the next lecture as well. And I expect that in the live session, you will ask, and you are actually invited to ask as many as questions as you like. Thank you very much. Allah Hafiz, and take good care of yourself.